Hello my dear students, today we will speak about the Faraday as a measuring unit. So the Faraday as a measuring unit, we have to measure the quantity of electricity and the relationship between the Faraday as a quantity of current of electricity, a quantity of electricity, a quantity of charges, and the equivalent mass, and the relation between the liberated mass and the actual mass which is liberated in relation to the quantity of electricity. In other means, okay, we have from Faraday's first law that the liberated mass of the substance directly proportional to the quantity of electricity, and the liberated mass of the substance directly proportional to the equivalent mass of this substance. If we combine between the two relations, we see that the liberated mass directly proportional to the quantity of electricity and the same liberated mass directly proportional to the equivalent mass. So the liberated mass here is directly proportional to the multiplication of quantity of electricity times equivalent mass. So here the quantity of electricity multiplied by the equivalent mass equals constant times the liberated mass. So as the liberated mass directly proportional to the quantity of electricity and the liberated mass directly proportional to the equivalent mass from Faraday's first law and Faraday's second law, then the liberated mass equals the multiplication of the quantity of electricity times the equivalent mass and a constant here. So we have the same relation, the quantity of electricity times the equivalent mass directly proportional to the liberated mass, or equals liberated mass multiplied by a constant. So the value of the constant we will deduce afterward. We will put the constant here under the quantity of electricity, and we put the gram equivalent mass or the equivalent mass under the liberated mass to have this form. The liberated mass of the substance over its equivalent mass equals the quantity of electricity over a constant. So what will happen when the liberated mass of the substance equals the equivalent mass? In this case, this ratio equals 1. On the other hand, in this case, the quantity of electricity will equal the constant. So the constant here will equal the quantity of electricity required to separate or deposit one equivalent mass of the substance. So what is this constant? We call this constant Faraday, and from this equation we can give the definition of Faraday. It is the quantity of electricity required to liberate. Liberate here means deposit, dissolve, evolve. It is the quantity of electricity required to liberate gram equivalent mass or an equivalent mass of the substance. So Faraday is a quantity of electricity. Quantity of electricity required to deposit or liberate equivalent mass of any substance. Okay? So let's have some examples. Calculate the quantity of electricity in Faradays required to deposit 21.6 grams of silver from silver nitrate solution, knowing that the reaction at the cathode, silver positive ion aqueous plus electron reduced to silver zero solid. And he gives you that in this example, silver atomic mass equals 108. So we know that 108 the equivalent mass, as the charge of silver is positive 1, so the atomic mass equals the equivalent mass. So the equivalent mass 108 grams will be deposited by using 1 Faraday, as the Faraday is the quantity of electricity required to deposit the equivalent mass of any substance. So what is the quantity of electricity required to deposit 21.6 grams? And by cross multiplication we'll find the solution. So 108 gram dissolved or required to be deposited 1 Faraday. So 21.6 grams, how much of Faraday does it require? Okay, cross multiplication, we find that the quantity of electricity equals 0.2 Faraday. Another example, on passing a quantity of electricity equals 0.5 Faraday, half Faraday, in an electrolytic solution. So 4.5 grams of element M are deposited. Calculate the equivalent mass of element M. By logic, half Faraday deposited 4.5 grams. So 1 Faraday deposited how much? 1 Faraday refers to the quantity of electricity required to deposit equivalent mass. So the equivalent mass, which is not known this time, requires 1 Faraday to be deposited. And 4.5 grams of this element, we know that from the example here that it requires 0.5 Faraday. So by cross multiplication it gives 9 grams. So by logic, half Faraday deposit 4.5 grams. So the equivalent mass, which is 1 Faraday, will deposit 2 times of this amount, 9 here. Okay, let's have another example. During electrolysis of copper 2 chloride solution, 3.2 grams of a substance are formed at the anode. So what is the number of moles of substance which is formed at the cathode? Here 3.2 grams of certain substance formed at the anode. The anode is the positive electrode, so it attracts the negative ions, the anions. Which of them here is the anions? Copper or chlorine? Chlorine is from a chloride which is anion, so it is oxidized on the anode, leaves two electrons from two chloride ions and oxidized into chlorine gas. So the anion here, the amount of anion here is chlorine. So he gives you here the equivalent mass of copper and the atomic mass of copper and the atomic mass of chlorine. That of copper, we want to calculate the equivalent mass from atomic mass. The equivalent mass equals the atomic mass over or divided by the charge of the copper. Copper here positive 2, as it takes 2 from halogen or from chlorine. So the equivalent mass equals the atomic mass over the charge of the copper over 2 gives 31.75. So the equivalent mass of copper, the quantity of electricity required to deposit or liberate the equivalent mass of copper, which is 31.75, which is half the quantity of atomic mass. The same quantity of electricity will liberate the equivalent mass of chlorine, which is 35.5, as the chlorine or the chloride only monovalent or negative 1 charge. So the equivalent mass of copper related to the equivalent mass of chlorine. The equivalent mass of copper here 31.75 and the equivalent mass of copper 35.5. So how much of the copper will be related to 3.2 grams of chlorine, which is liberated at the anode? So this is one idea of solution. The other idea, that we can put it in the same relation of the second Faraday law. the formed mass over the equivalent of its equivalent mass, or the first substance, the formed mass of the first substance over the its equivalent mass equals the formed mass of the second substance over the equivalent mass of the second substance. This is a direct relationship, so this is a direct substitution in the relation. So the formed mass of copper is required to be calculated. The equivalent mass of copper is atomic mass over 2, the charge of the copper, and the formed mass of chlorine here is 3.2, and the equivalent mass of chlorine is 35.5, as the equivalent mass of chlorine equals its atomic mass, as the charge of chlorine is only 1, of chloride is only 1. This is another way. Okay, let's speak about the relation between the Faraday and Coulomb. We know that 1 Faraday is required to precipitate, deposit, or liberate the equivalent mass of any substance. So we will use this definition to calculate how much Faraday, the quantity of Coulomb, the quantity of charge, or the quantity of electricity in Coulomb, how much it equals 1 Faraday, how much of it will equal 1 Faraday. So 1 Coulomb by experiment deposits 0.001118 grams of silver. So how much of Coulomb, how much of electricity in Coulomb will precipitate 107.88, which is the equivalent mass of silver. So the quantity of electricity which will deposit 107.88 grams of silver, which is the equivalent mass of silver, equals 96,500 Coulomb. So 1 Faraday will deposit 107.88, as it is the equivalent mass of silver, and 96,500 Coulomb will precipitate the same amount. So by this we will understand that 1 Faraday equals 96,500 Coulomb, and this is the general law of electrolysis. The general law of electrolysis states that the general law of electrolysis states that 1 Faraday, which equals 96,500 Coulomb, if it passes, or if we pass through an electrolyte this amount, which is 1 Faraday, amount of electricity 1 Faraday, or 96,500 Coulomb, it will precipitate, liberate, dissolute, or evolute, or deposit 1 equivalent mass of any substance. So let's have it another time, speak about it another time. 1 Faraday, which equals 96,500 Coulomb, if it passes through an electrolyte, so it will cause the liberation of the equivalent mass of any substance on any of the electrodes. So this is the general law of electrolysis. So here we want to calculate the equivalent mass of an element. It equals the atomic mass, as we have said before, the atomic mass over the number of charges of the same element. So here we want to make some applications. The calculations of quantity of electricity required to liberate the atomic mass of any substance or some substances, some common substances, which we will use in calculations of a lot of problems. Okay, here the quantity of electricity required to deposit 1 gram atomic mass or atomic mass of silver. Now silver reduced by taking only 1 electron, so 1 mole of silver take only 1 mole of electrons, so 1 mole of electrons related to 1 Faraday. So if the equation takes 1 mole of electrons, so it means the same amount of as mass will require 1 Faraday. So 1 Faraday will deposit 1 mole of silver, as the equivalent mass of silver here equals the atomic mass. So here's the quantity of electricity required to deposit the atomic mass of copper. We will calculate the copper here, positive 2, require 2 electrons, 2 moles of electrons. Each 1 mole of these electrons require 1 Faraday to be liberated at any electrode. So 2 electrons, 2 moles of electrons require 2 Faraday. 2 Faraday equals 2 times 96,500 coulomb. So here aluminum positive 3 requires 3 electrons, 3 moles of electrons. Each mole of electron require to be precipitated or deposited or liberated at any electrode require 1 Faraday. So 3 moles require 3 Faradays. So this quantity, which is aluminum, 1 mole of aluminum, 1 atomic mass of aluminum 27 requires 3 moles of electrons, means requires 3 quantities of Faraday as a measuring unit. Each 1 Faraday equals 96,500 coulomb. So the atomic mass of aluminum requires 3 of Faraday, or requires 3 times 96,500 coulomb. So this is the calculation of quantity of electricity required to evolve 1 mole of some gases. Here we have to know that these gases are diatomic gases. It is not monoatomic. So we have to calculate the amount of moles of electrons which is required to liberate 1 mole of this gas or of any gas. So there is gases with tetraatomic molecule, octaatomic molecules. So we have to know that how much 1 mole of this gas will require from electrons. How much moles 1 mole of gas require from electrons, from moles of electrons. So 2 hydrogen ions here require 2 electrons, 2 moles of electrons to require 1 mole of gas. So 1 mole of gas here required to be formed at any electrode requires 2 moles of electrons. It requires 2 Faradays, which equals 2 times 96,500 coulombs. Here oxygen go to the anode, release 4 electrons, 4 moles of electrons. So 1 mole of oxygen, when it is formed at the anode, releases 4 mole of electrons, means requires 4 moles or 4 Faradays, which equals 4 multiplied by 96,500 coulomb. And at this time we go to the end of this session. Thank you.